After the short overview of clustering in this notebook, we will learn how to perform clustering using scikit-learn in Python. We will use cluster analysis to generate a big picture model of the weather at the local station using a minute granularity data. In this data set, we have in the order of millions of records. It's a large data set, largish data set for some of us. Our goal will be to create 12 clusters from them. So let's first import all the necessary libraries. Note that, again, it's common to import libraries as you keep working down in the notebook. You don't have to import all the libraries at the beginning, like we did for the classification notebook. But it's cleaner and easier for the end user of your code to understand what the dependencies of these notebooks are. So I'm just going to go ahead and do it on top here. We now import the minuteweather.csv into pandas. Hope you were, by the way, able to locate your weather data clustering using k-means in your package, and also the minuteweather.csv in the weather folder for week 7. So we are importing it and calling our data frame data. Okay. Each row in this data frame will contain measurements at the minute interval. The minute weather data description in this markdown here describes the data set, the timestamps, what air pressure means, what kind of units are there for our data, and things like that. Let's quickly actually see the shape of the data after you read through the markdown. Hopefully you're back in the video. We see that there are over 1 million records in this data set, 1.58 million records. And then 13 rows, which are described right above, from row ID to average wind speed to relative humidity. We should also check our understanding of the data description by exploring with the data frame. I use the head function here shortly to get the first 5 rows of the data, to look at the data values and maybe have a feeling of the null values. But I, as usual, encourage you to stop the video here and execute some more exploratory data queries and slices over this data so you'll have a better understanding of the data before we move on. This is a very important step for any analysis, and I would not like to underestimate that step. So hopefully you're back and you explored with the data, you have a good understanding of it now, and you already know that the data set is large. For analysis sake now, we can further sample this data down to maybe every 10-minute difference. Instead of 1 minute, we'll do 10 minutes. Here, we assign the data sample to a data frame called sampled_df, sampled_df. So what we are doing is we are getting the row ID and dividing it by 10. So we are getting every 10th data frame, every 10th row compared to our original data set. So sample_df will have 1/10 of the number of rows in the original data set after we do this. As we see here, we have about 158,000 rows now instead of 1.58 million. So let's describe this data set. I'm transposing here when we say sample_df.describe.transpose. Recall, if I didn't say transpose actually, the original columns would be displayed as columns. The transpose operation that we did, let's go back and do that, turns the columns into rows and vice versa, the rows into columns. After the describe operation completes, let's check out some things, right? Let's check out the mean values of each measurement. Let's not worry about the row ID, it's an identifier, but let's say the mean for air pressure is 916, air temperature 61 in Fahrenheit, average wind direction is 162 degrees, and things like that. We notice that some readings are in hundreds, while others are in decimals. It's a large difference, especially if you make it a measure of clustering when you're creating clustering metrics. Let's see how many rows have the value 0 for columns, for rain accumulation and rain duration, for example. Rain accumulation is how much it rained and accumulated. And rain duration is how long it rained for. Here, we select all the rows that have value 0 for these two columns. Right? Sample df, rain accumulation, and sample df, rain duration. And we check if they're equal to 0. And we select those rows that we just selected from the sample df. And then we look at the shape of the resulting data frame. We have about 157,000 rows out of 158. So it looks like a significant number of rows are 0 compared to the size of the data. So I'd say let's drop these columns and also clean any missing values for data cleaning. So we'll delete sampled df, rain accumulation, and rain duration because they were mostly 0. And we also here drop the null values. Rows before will show how many rows our data frame had before dropping the null values. Rows after will show how many rows are left after dropping the rows with null values. So how many rows did we drop? It's about 46. In the end, let's see what columns are left in our sample df data frame. Right? Let's remember our columns now. So we have the row ID, timestamp, air pressure, air temperature, and down to the relative humidity there. Out of these features, we will now select a list of features to declare the columns that we want our algorithm to make use of. Let's store those features in a list that I'll call features here. Air pressure, air temperature, wind direction, wind speed, maximum wind speed, average wind speed, two of them, and the relative humidity. Great. Out of these features, we will now select a list of features to declare the columns that we want our algorithm to make use of. Let's store these features in a list which I'll call features, simply. And as we did in our classification notebook before, you might have recognized the approach. The features we select here are air pressure, air temperature, average wind direction, average wind speed, max wind speed, and relative humidity. So out of about 11 columns, we are selecting about 6. So let's look at this, what we have. We'll use these features to create a data frame called select data frame. So remember, we had our data. We put it in the sampled data frame, which was the 10th of our data. Now we are reducing the data, the number of columns in the data, not rows. We get these 6 columns that we listed in the feature and put it in select df. When we looked at the columns of the select df, we'll see those 7 columns, not 6, apologies. And if you look at the data frame itself, we'll see the data nicely copied over into this Neve data frame. Okay. Now, remember our scalability or scale discussion. To keep values of different columns comparable, we scale the values in these features. So we will use standard scaler for that. It's an object, and if we give a data frame to it, to a function of it in this case, we'll get a nicely scaled input data for our clustering operation. So we have the standard scalar, and we use the fit transform function of it, and we give the select df that we just created as an input to that. Okay? The fit transform function here combines fit and transform operations, which means it first calculates how much the data set should be transformed to be scaled. So it looks at different values and finds how to scale that. Then it's going to apply that transformation to the data frame we give it, in this case select df. And it's going to apply the transformation it came up with to that data frame. We will assign the output of this function to x, just like we did here. And that x that we are creating in a nicely scaled fashion will be an input for our k-means modeling later. Okay, let's scale select df and assign it to x. And if we display x, we see the nicely scaled values there. They are not the values here anymore, right? They are at a certain scale between a minimum and a maximum number. So feel free to explore x further and compare maybe to the other operations, other values in the select df. And when you come back after that, we'll start k-means clustering. Okay, now we will start with invoking the k-means clustering algorithm. Remember our original purpose, to create 12 clusters. And we'll use the scale data frame x with the selected features as an input. As you see here, we created a k-means object called k-means, and we set number of clusters for it as 12. And the model was generated by using the fit operation of that k-means object, and the input for it was our input data x, which was the scaled version of the selected data values. If you look at the type of this model object, it is a k-means object still. Okay? Note that we use 7 features to perform clustering. Those are stored in our features list. Once clustering is done, we can now look at each of the cluster centers. It will be a list of 7 floating point numbers, which denote where the cluster center stands in the 7 dimensions of our feature space. Okay? So we'll assign that to a variable object called centers. So we are getting the model and assigning the cluster centers of that model into centers, which will be an array. For each 12 clusters, it will have those 7 values that represent the cluster center. We use the attribute cluster centers for that, right? It was the attribute of the model. When we created the model up here, it actually was stored as a part of that model. It's great. We have now the cluster centers for each 12 clusters, but how do we interact with it? How do we visualize it? Right? It would be great to plot these cluster centers so we can actually examine which clusters are close to each other and what separates different clusters from each other. For these, here we will create 2 functions that help us transform the data to make it easier for plotting. Function 1 here is called PD centers. It takes in the cluster centers generated by the model, the ones that we just displayed in centers, and creates a pandas data frame, returns P, where the header is the name of each feature. It also adds a new column that denotes the number of the cluster itself. This new column here is called prediction. Okay? So we have the cluster centers and the number of the cluster nicely in a data frame, and we return that as a part of this function. The second utility function we have here is for plotting, and it's called parallel plot. It takes in the data for plotting, which is the data frame that we just generated actually out of this PD centers, and generates a colorful graph with different colors to each cluster. So if you stop the video and explore this a little bit, you will recognize some of the plotting features you learned in our earlier weeks. This function, note that it also sets the size of the plot and controls the range of the y-axis. If you look at that, we have the figure size and the y-axis limits. Okay, a parallel coordinates plot is a quick way to visualize cluster centers along all the 7 dimensions of our feature space. That's why we created these functions. So let's run them. And first, we'll give the features and the centers to PD centers. And we'll get that nice data frame that we generated. So remember, centers had a value for each feature for each cluster. So each of these values is the cluster center, make up the cluster center for that particular cluster. We give it this, but this one doesn't have the information on those features. The names of, or the labels, column labels of each value here is in the features list. That's why we give both the features used and the centers to PD centers. And the PD centers we've done will create a data frame for each and label each data frame also with the cluster number. So it's going to add to the features a, if we display this, it's going to add to these features a cluster number as well. Let's rerun this. So we see all 12 clusters, 0 to 11 here in the rows, the features we selected, and also the prediction, the number of the cluster it was done for, which is equal to our row in this case. Okay. So now we are creating a parallel plot using this P for, let's say, the cluster where relative humidity is less than minus 0.5, right? Notice that the x-axis denotes each of the 7 features we use for clustering, the values for them. And the y-axis denotes the values of each cluster center. So we have the labels in the x-axis for the features and the values in the y-axis. We can now, after we plotted them, we can compare these clusters. Which clusters are similar, which are not. Remember, we are doing clustering for the features we selected in the features list, including relative humidity, like we selected here, and air temperature. For each of the 3 plots, we show dry days, relative humidity is less than 0.5. Warm days, the air temperature is above 0.5. Remember, this data is scaled. And cool days, which show the relative humidity above 0.5. So these are the clusters that have the behavior, so to say, of dry days, warm days, and cool days. And the cool day is a combination of relative humidity above 0.5 and air temperature below 0.5. For example, let's look at red and blue clusters in each graph. If you follow the cluster line for red and blue clusters in each graph, you can notice that they're close to each other for a few features and far apart on others. If they differ on a particular feature, this is one of the features which is likely helpful to distinguish this cluster from others. For example, red and blue are pretty far here, far here, far here, closer here. So they are pretty different two clusters, right? They are different clusters, but how different and which features are different for, this plot will help us to identify that. For the dry days graph, the differences are in, as we looked at, air pressure, air temperature, features related to wind speed. So they are pretty different. Let's look at the warm days, if they are closer than for dry days. If you follow the two lines and look at the labels, looks like they actually differ for all features related to wind. And in the cool days graph, they vary for most features, if you look at that, related to wind speed, right? These are pretty similar up to the point. The moment we look at average wind and maximum wind speed, we see that they are different. So remember that these parallel feature plots are really useful for analyzing clusters which we have high dimensionality of features to gain an intuition about how these clusters differ. Feel free to play around with this notebook more to see if you can get a better feel for what each cluster is from a weather standpoint. To me, for example, cluster 4 seems to correspond to hot and dry days with fairly stagnant air. So just look at them and try to imagine the air on that day and how you could further now use this information.